Welcome all. In this particular lecture of the statistical mechanics, we will discuss about ideal Fermi gas. So, before I start the lecture, I would like to say that before going through this particular lecture, you should have some preliminary knowledge regarding some of the topics. So, what are the topics? You should have some knowledge about the statistical distribution. Statistical distribution means you should know, that is, what do you mean by Fermi distribution function, what do you mean by occupation number in the case of FD statistics. You should know, that is, what is Bose-Einstein distribution function, what is the expression for the occupation function for Bose-Einstein distribution. So basically you should go through the chapter statistical distribution at first, and I have a lecture regarding this statistical distribution, so better you listen that lecture at first. And you should also have some knowledge about the concept of the partition function and grand partition function. These topics we have also discussed earlier in the canonical ensemble and grand canonical ensemble. And you should have known that from the expression of the partition function, from this expression we can calculate different thermodynamical parameters. So once we know the expression of the partition function, then we will be able to calculate the expression for the different thermodynamic variables. So these are the topics you should know at first, then you should go through this discussion. Now ideal Fermi system. So this particular topic will be divided in some parts. So this is part 1 of the discussion, and in this particular lecture, that is in part 1, what we will discuss about the mathematical concept, mathematical preliminaries that we will use for studying the ideal Fermi system. So we will discuss the mathematical preliminaries, and we will discuss the Fermi system in classical cases. So these topics will be discussed in this particular lecture. So let me discuss about the mathematical preliminaries. Now here I would like to say that in our earlier lecture, that is was about the Bose-Einstein condensation and ideal Bose system and its thermodynamical properties. So there we have learned about some mathematical techniques. So those techniques will be again used here. So you should have some idea about the mathematical techniques that we have used for studying the ideal Bose system. Same techniques, same types of techniques will also be used here. So again I would like to request, that is, you go through the topic about the ideal Bose system. So let us define a particular function f nu z, capital F nu z, that is defined by this integration, which is 0 to infinity x to the power nu minus 1 dx divided by z to the power minus 1 e to the power x plus 1. Now this particular function is similar to the Bose function capital G nu z. I have already said that is exactly same types of mathematical techniques will be used here. So similar to the Bose function capital G nu z, here we have defined a function capital F nu z. Now you have to look very carefully, that is you see that here what is the limit of z. Here the limit of z is from 0 to infinite. So the limit of z is different for Bose system and Fermi system. And so for nu greater than 0, the limit of z will be from 0 to infinity. Now this is the expression for the f nu z. And another function that is similar to the both cases, we can also define another function small f nu z. So what is small f nu z? Small f nu z is equal to 1 by gamma nu is equal to into capital F nu z. This is also similar to the case of Bose system. There we have used the function small g nu z. So just similar to the Bose system, small f nu is the Fermi function. So small f nu z is equal to 1 by gamma nu into capital F nu z, and that is equal to 1 by gamma nu 0 to infinity x to the power nu minus 1 dx divided by z to the power minus 1 e to the power x plus 1. Now when the value of z is small, then this particular integration can be performed in this way. So 1 by gamma nu 0 to infinity x to the power nu minus 1, that will remain unchanged, and the other factor, that is 1 divided by z inverse e to the power x plus 1, this particular factor can be expressed in a power series. So how we can express that particular function in a power series? I will refer again to the Bose system, and I in that particular lecture I have already shown that is how this particular function, that is 1 divided by z inverse e to the power x plus 1, how that particular function can be expressed in this power series. So I would like to request to view that lecture. So this particular function can be expressed in a power series like that: L is equal to 1 to infinity minus 1 to the power L minus 1 z into e to the power x to the power L dx, where the limit of L is from 1 to infinity. Now if you evaluate this integration for different values of L, then we will obtain this type of power series, that is f nu z is equal to z minus z square by 2 to the power nu plus z cube divided by 3 to the power nu, in this way. And it can be mentioned, that is for z very less than 1, the function f nu z for all values of nu behaves like z itself, because it is very easy to understand, because these are powers of z square, z cube, z to the power 4 and so on. So if the value of z is small, then these particular powers of z, that is z square, z to the power q, these higher powers of z can be neglected, and we can assume that is f nu z is approximately equal to the value of z. This particular behavior is also similar to the case of Bose system, and the only difference is that in this particular power series the signs are alternately minus and plus. And this particular Fermi function f nu z, they can be related to the Bose function g nu z by this particular formula. So this is the particular formula which relates the Fermi function with the Bose function. Some particular integration will be used when studying the Fermi system. I am not discussing this in details, but when we will go through those particular topics, then we will again come to this particular point. So these are the some standard integration which will be used when we will study the Fermi system. And there is a recurrence relation which is quite similar to the case of Bose system. This recurrence relation we have also used when studying the Bose system. So this is a recurrence relation, that is z into del z of f nu z, which is equal to f nu minus 1 into z. This is the recurrence relation. To study the behavior of the Fermi-Dirac integrals for large z, when z is large. So one case we have already told, that is the Fermi function f nu z is equal to z for large values of z, but for small values of for small values of z, f nu z is almost equal to z, but for large values of z we can convert the Fermi integrals by introducing a variable zeta is equal to ln z. So when we put zeta is equal to ln z, then that particular Fermi function f nu e to the power zeta. So you see that in place of z we have written e to the power zeta. So f nu e to the power zeta, that will be gamma nu into f nu e to the power zeta, and this is equal to 0 to infinity x to the power nu minus 1 dx divided by e to the power x minus zeta plus 1. So you again look at the structure of the function. So this was actually the expression of the function f nu z. There we have introduced a variable. That is zeta is equal to ln z, or z is equal to e to the power zeta. So this particular substitution has been performed in this particular integration. After the substitution, the Fermi functions look like this, that is f nu e to the power zeta is equal to gamma nu into f nu e to the power zeta is equal to 0 to infinity x to the power nu minus 1 dx divided by e to the power x minus zeta plus 1. So this is the structure of the Fermi function. Now the thing is that if you consider large zeta, so this is very important, that is we are saying that is for large value of zeta, this particular integrand is primarily controlled by the factor e to the power x minus zeta plus 1 to the power minus 1. So the value of the integrand is primarily controlled by the factor of this. So when we will study the behavior of the Fermi function, then we will mainly focus on this particular expression, that is 1 divided by e to the power x minus zeta plus 1. Now you see that is how this Fermi function depends on the values of x. So this is the graph. So you see in the y-axis, although it shows the behavior of the Fermi function capital F, but we have primarily shown this particular factor, as we have earlier said, that is this particular Fermi function is mainly controlled by this factor only. So in the y-axis we have shown this factor, and in the x-axis this is the variable x, and that is basically zeta. So in the x-axis we are varying the values of zeta. In the x-axis we have showing the variation of the variable zeta. Now you see this particular factor e to the power x minus zeta plus 1 to the power minus 1. Now for very small values of x, for very small values of x we will show the variation, and for large values of x we will show the variation. So you see that is suppose x tends to 0. So if the x tends to 0, then what will happen? The value of the Fermi that is this particular factor will be almost 0. So ultimately the value of this particular factor will be 1. So this is one case, that is when x is equal to 0, the value of this particular function will be almost 1 when zeta will be very large. This is the main thing, because you see suppose you focus on this particular factor e to the power x minus zeta. Now suppose x is equal to 0, then it will be e to the power minus zeta. Now e to the power minus zeta means 1 divided by e to the power zeta. Now as you have assumed that is value of the zeta is very high, so 1 divided by e to the power zeta, that will be almost 0, and if this is almost 0, then ultimately the value of this function will be 1. That is why for x is equal to 0 and the value of this function is 1. Now another point is that is when x is equal to infinity. when x is equal to infinity. So when x is equal to infinity, what will happen? When x is equal to infinity, then it will be e to the power infinity minus zeta, that means almost e to the power infinity. Now if this first function, that is first function is e to the power infinity, so ultimately that will be e to the power infinity plus 1 to the power minus 1, means 1 by infinity, that means 0. So for the value of x equal to infinity, the value of this particular function will be 0. So these are the two limits of this particular factor, so that is 1 and 0. So therefore we have shown that is for x is equal to 0, the value of this function is 1, and for x is equal to infinity, the value of this particular function is 0. Now we have shown the value of x that depends on zeta. For example, you see that this particular point is x is equal to zeta. This point is very important, because you see if we put x is equal to zeta here, then the value of this particular function will be half, because e to the power 0, that means 1. So 1 plus 1 to the power minus 1, that means half. So you see for this particular value of x that is equal to zeta, this value of this particular factor is half, 0.5. And these are the particular points that shows the values of x for some higher values of zeta. For example, this point is x is equal to zeta, this one is x is equal to zeta plus 2, this one is x is equal to zeta plus 4, and in the left side this is zeta minus 2, and this is zeta minus 4, and so on. So these are the different points which are different values of x in terms of zeta. So you see that is the value of this particular factor varies from 1 to 0, and the deviation from the limiting value occurs some points earlier than zeta to some points that is beyond zeta. You see that this from here the deviation from the maximum value 1 starts. So this is the starting point of the deviation, and ultimately this deviation goes like here, and here we approach to the limiting value 0. So this particular deviation, that is from the maximum and minimum value, so this particular deviation occurs in this particular region. In this region, this particular deviation occurs. Now you see that is what is the width of this function. The width of this function is 1, because you see lower value is 1, lower value is 0, and upper value is 1. So width of this particular function is 1, whereas you see that is in the x-axis. In the x-axis we have shown the variation of x in terms of the zeta. So you see that is variation of x starts from 0 and ultimately it goes to infinity, and the value of zeta is very high. You see we have already said that is the value of zeta is very high, and this particular deviation occurs in this particular region. Now you see that is the variation of x, it has been shown in the region 0 to infinity, and value of the zeta is very high, and in the graph we have used this particular symbol. You see we have used this particular symbol. So meaning of the symbol is that actually the range of this particular portion is very high. So that is why we have shown here. That means this is a continuation of the graph, but here we have shown a small portion of the variation. But the point is that as the value of zeta is very high, if we compare this width is 1, but compared to 1 the value of zeta, that is this particular position is very high, value of zeta is very high. So these points are very close, that is value of zeta is so high this is zeta plus 2, this is zeta plus 4, this is zeta minus 2 and zeta minus 4. These points will be very close to each other, and as the value of the zeta is very high and we are showing this graph in the region 0 to infinity, so this particular deviation in the graph will not be very high, and in this particular graph this particular deviation we can ignore. So basically this particular graph can be approximated like a step function. You see, we have shown a dotted curve instead of this particular deviation. So when we will plot the graph, this particular deviation will be negligible. That is why we have shown this particular dotted graph. That means this particular graph can be approximated, but approximated when we will consider the value of zeta is very high. When value of the zeta will be very high, then these points will come close, and it is very difficult to visualize this deviation. Now you see this limit of the integration is 0 to infinity. So we can divide the limit in two parts. The first part is 0 to zeta, and the next part is zeta to infinity. Now when we will consider the region 0 to zeta, then the value of this function, that is 1 divided by e to the power x minus zeta plus 1, value of this particular function will be 1, because you see in the graph, that is if we consider the range 0 to zeta, then the value of the function is almost 1, and after the point zeta the value of the function becomes 0, because as we are approximating this particular function as a step function, so in the region 0 to zeta the value of this particular factor will be 1, and after the point zeta the value of the factor will be 0. So this particular integration, when we will consider the range 0 to zeta, that will give us only x to the power nu minus 1 into dx, because the other factor is 1. So this particular Fermi function can be approximated like this. So this is zeta to the power nu by nu. This is the approximation of the Fermi function. So if this is capital F nu, then small f nu e to the power zeta will be zeta to the power nu divided by gamma of nu plus 1. Another approximation can be done. So this is a straightforward method, but I am not going to discuss the details about the method, but I will show you the final result, that is f nu e to the power zeta, that can be written by this power series. So this is another approximation of the Fermi function. So Fermi function can be approximated two ways. So one way is the procedure that we have already discussed, and the another method is like this, that is we have to integrate the function in a straightforward manner, and ultimately you will obtain a series like that, and this series we will also use when we will study the Fermi system. Now I am coming to the discussion of the ideal Fermi system. So let me show you two equations. The first equation is this one, equation 1, and this is the second equation. Now here I will say, that is you see these equation 1 and 2 we have already studied when we discussed the Bose system. In case of Bose system also we started our discussion by these two equations. And how we have obtained this equation? We have obtained this equation in the chapter statistical distribution. There we have derived these two equations. So I will refer to that lecture if we want to see, that is how we have obtained these two equations. So here the term beta is equal to 1 by kt, and the value of z is equal to e to the power mu by kt, where mu is the chemical potential. And unlike the Bose case, the parameter z in the Fermi case can take the values from 0 to infinity. So in the Bose system the value of z was from 0 to 1, but in the case of Fermi system the value of z is from 0 to infinity. Moreover, in view of the Pauli exclusion principle, the question of a large number of particles occupying a single energy state does not even arise in this case. So, Fermi system is different from the Bose system. In the Bose system, we have learned that in the ground state, several number of particles that can come down, and this results in the Bose-Einstein condensation. But here there is no phenomena like the Bose-Einstein condensation, and ground state cannot be occupied with a large number of particles. And the behavior of the Fermi gas, so Fermi gas actually displays its own brand of quantum behavior, and a detailed study of which is of great physical interest. So the behavior of the Fermi system and Bose system is different. Now just like the Bose case, what we can show that this particular summations can be replaced by the integration, and for this replacement we will proceed in the same manner that we have adopted for studying the Bose system. So we can show that from equation 1, P by kt is equal to g by lambda cube f 5 by 2 into z, and from equation 2 we can show n by v is equal to g by lambda cube f 3 by 2 z, where small f is the Fermi function that I have already introduced, that is what is the Fermi function, and small g is a weight factor arising from the internal structure of the particle, that is spin, and here lambda is the mean thermal wavelength of the particle. And how we have obtained equation 3 and 4, so that particular technique we have already discussed in the case of Bose system. So I will refer you to listen that lecture, and you will understand that is how equation 3 and 4 can be obtained from equation 1 and 2. So this is the expression of the thermal wavelength of the particle, and this is the expression of the Fermi function which we have already discussed. Now you see that is from equation 3 and 4, if you eliminate z, then you will obtain a relation between p and v and n. So that is the basically the equation of state, and I will show you that is how the equation of state looks like. But before that, we will calculate the value of the internal energy capital U. So we can calculate the internal energy U from the partition function. So here capital Q is the partition function. So what is capital Q? Capital Q is this one, that is PV by KT is equal to ln Q is equal to this one. So the value of internal energy can be calculate from the expression of the partition function. So this is the formula, required formula, which we have studied in the case of grand partition function, which we discussed in the chapter grand canonical ensemble. So using that particular relation, that is U is equal to minus del del beta of ln Q, and this particular relation is same as if you write this particular expression in this way, that is kt square del del t of ln Q. So after the differentiation of the function ln Q, we can obtain that is 3 by 2 kt gv by lambda cube f 5 by 2 into z. So by differentiating equation 1, we have obtained a value of the internal energy U, which is this one. Now this particular factor, that is gv by lambda cube, that is f3 by 2z, that can be written in terms of the gv by lambda cube. So we have omitted the term gv by lambda cube, and we have written here 3 by 2 nkt f5 by 2z by f3 by 2z. So why f3 by 2z can be written as gv by lambda cube, that we have also discussed in the case of Bose system. Just following that formalism, we are writing that is f3 by 2z is equal to gv by lambda cube. And another thing is that is we have also used this particular relation. You see equation, this equation, that is f3 by 2z, that can be written as n by v into lambda cube by g. So from this relation also we can write the expression of f3 by 2z. So you see that is instead of Gv by lambda q we have used this one, that is from using the equation 4. Using equation 4 we have written u is equal to 3 by 2 nkt f 5 by 2 z divided by f 3 by 2 z. Now this is the expression for the capital U, and this is the expression of the capital P. Now from equation 3 which shows the expression of the pressure, and from equation 7 which shows the expression of the internal energy U, from this two equation we can easily show that is P is equal to 2/3 U by V. So using equation 3 and 7 we are showing that is P is equal to 2/3 of U by V. Now we can calculate the specific heat from this equation 7, because we know that is the formula of the specific heat Cv is equal to del U by del T. So if we differentiate equation 7, then we can obtain the value of the specific heat. But one thing we have to keep in mind, you see that the right hand side of equation 7 that contains the term z. So when you will differentiate f5 by 2z with respect to t or f3 by 2z with respect to t, then you need the variation of z with respect to t. So there is a formula 1 by z del z by del t, that is equal to minus 3 by 2t f3 by 2z divided by f half z. So this particular formula we have already shown in the case of Bose system. So this formula will be used when we will calculate the differentiation of the equation 7, so that is del U by del T. Now by proceeding in the same manner as we have adopted in case of Bose system, so we can show the value of the specific heat is like this: Cv by Nk is equal to this one. So again I will refer to listen the lecture regarding the ideal Bose system. There we have derived the formula of the specific heat. So that derivation you have to look very carefully. Using the same techniques we can derive the expression for the specific heat by equation 10. So for the derivation, if you want to see that is how we have derived this, then I will refer to listen that lecture. There we have demonstrated that is how we can calculate the value of the specific heat from the expression of the internal energy. So this is the expression of the specific heat. Now Helmholtz energy A, that is given by n mu minus Pv. Now what is now we can write mu in terms of z, because we know that is z, small z, that is equal to e to the power mu by kt. As z is equal to mu by kt, so we can write n mu as n kt ln z. And what is Pv? You see that is the next term Pv. So Pv is equal to 2/3 of u from this relation, and you have already evaluated the expression of u here. So Pv is equal to 2/3 u. So from that formula, using equation 7, we have written the second term. So this is the second term, and the entropy is u minus a by t. We know this particular thermodynamic relation. So there we can calculate the value of the entropy S from the expression of u and a. So using the expression of u and a, we have obtained the expression of the entropy in equation 12. Now these different thermodynamic variables, that is specific heat, Helmholtz energy, entropy, all depends on the parameter z. You see in the right side there is z. So if we want to know the variation of these different thermodynamical parameters, then we need to know the functional dependence of the parameter z on small n and capital T. So if we know the functional dependence of z on small n and capital T, then we can say that is how different thermodynamical parameters varies with respect to the temperature. And one thing to note, that is this information is formally contained in the implicit relationship 4. You see the equation 4 again, you see n by v, that we can write small n. So you see this particular equation 4, and that is the dependence of z on the value of the particle density small n. So this particular relation gives you the dependence of z on small n. And we also know the how to express f nu z, that we have already discussed in our mathematical preliminaries. So from those concepts we can study the behavior of these different thermodynamical functions. Now we will discuss different cases. In the beginning of the lecture I have said that is in this particular lecture I want to focus on the classical case. So if the density of the gas is very low and its temperature is very high, then the situation might correspond to f3 by 2 z, that is equal to n lambda cube by g. Why I have written f3 by 2 z is equal to n into lambda cube by g? This is from equation 4, because you see this particular n by v, that can be written as small n. So f3 by 2 z will be n lambda cube by g. So f3 by 2 z is equal to n lambda cube by g. Now if we evaluate lambda in terms of temperature, then the expression will look like this, because you know the expression of the thermal wavelength, which we have already shown in the beginning of the lecture. So expressing the thermal wavelength in terms of the temperature, this expression will look like this. Now as you have assumed the temperature is very high, that means the denominator is very high and the density of the gas is very low and the numerator is very low. That is why this particular expression will be very less than 1. So this is the case of classical gas. We then speak of the gas as being non-degenerate. The first thing is that this particular case will be regarded as non-degenerate case and therefore equivalent to a classical ideal gas. So this is the same as classical ideal gas, and the case is the case of non-degenerate. This is a non-degenerate case, and these things we have already discussed when we have started the statistical distribution. Now you see that is in view of the expansion 6, that is in the equation 6 we have shown that is how we can expand f nu z. The expansion of f nu z is equal to z minus z square by 2 to the power nu plus z cube by 3 to the power nu, etc. Now if we consider the value of z is very less than 1, then we can ignore the higher powers of z and f nu z can be approximated as z. So f nu z is approximated as z. So this is the approximation, that is f nu z is z. Now if f nu z is z, that means for any value of nu, this is true for any value of nu. So if we can write f nu z is equal to z, then the expression of the different thermodynamical variables which we have already derived, you see we can start from this expression. That means, for example, suppose u will be 3 by 2 nkt only, because you see f nu z is equal to z, so numerator and denominator will be same, both will be z, so u will be only 3 by 2 nkt. This is the expression of the u. Next is that for example, if you know the expression of u, then pv will be 2/3 of u, p into v, that will be 2/3 of u. So you can also calculate the value of pv. So pv will be nkt, p into v is equal to nkt. That is the equation of state in case of ideal gas, classical ideal gas. So pv is equal to nkt and u is equal to 3 by 2 nkt. And if u is equal to 3 by 2 nkt, then definitely Cv will be del u by del t. That means Cv will be 3 by 2 nk. You can also evaluate Cv from this formula also. Here the numerator and the denominator all will be z. So Cv by nk will be only 15 by 4 minus 9 by 4. Ultimately it will give you Cv is equal to 3 by 2 nk. And for this case, that is for A and S, again you can show that is, for example, this particular factor that will be 1, because f5 by 2 z, that is z, again f3 by 2, and that is also z, so z by z is equal to 1. This factor will be 1, so we will replace this factor will be 1, and this whole factor will be 5 by 2, and for place of z, you can write down the value of z. Value of z is n lambda cube by g. Why? Because f3 by 2 z is equal to z when z is very less than 1. So we can express the value of z by using this expression, because f3 by 2 z, that is equal to z. So z is equal to n lambda cube by g. So in this expression of a and s, for z, we can use this expression n lambda cube by g. So that is why you see, that is in place of z we have written n lambda cube by g. Other things will be governed by the equation, that is f nu z is equal to z. So these are the expression of a and s in case of classical and non-degenerate case. Then another thing is that if the parameter z is small in comparison with unity, so we have assumed that is z is very less than 1, but it can happen that is z is small in comparison with unity, but not very small, then what will happen? And then we should use the series 6, because in the equation 6 we have shown that is what will be the expression of f nu z. Here you will obtain some more powers of z, because you have assumed that is z is not so small, so we will obtain some powers of z. And if you express f nu z with this particular series, then you see from these two expressions, that is equation 3 and 4, we can eliminate z. But for elimination you have to use this particular power series. Then you cannot use the approximation, that is f nu z is almost z. You have to use this power series, but still you have to eliminate z from these two equations. So in that case you will obtain a particular equation that is the equation of state, which is in the form of virial expansion. So this particular form of equation of the state will be in the form of virial expansion. So that virial expansion we have studied in case of ideal Bose case also. So just following that mathematical technique, what we can show here, we will not study the detailed mathematical procedure, but we can say that is we are adopting the same mathematical technique which we have used in ideal Bose gas. So following that same technique, we can show that PV by NKT, that is equal to minus 1 to the power L minus 1 AL lambda cube by GB to the power L minus 1, where L is equal to 1 to infinity, and AL are some coefficients, the values of the coefficients which we have already discussed in the case of Bose gas. So expressions for the AL is same. So this is the expression of the equation of state, that is PV by NKT. And if you know the expression of PV by NKT, you can also calculate the CV, because we know the CV is equal to del U by del T, and U is also related to P and V, because we have already shown that is P is equal to 2/3 U by V. So if you know PV, then PV is equal to 2/3 of U. From that relation you can also calculate the value of the specific heat. So value of the specific heat in virial form is like this. So if you put the values of L starting from 1 to infinity, so this particular series will look like this. Equation 18 is the expression for the specific heat in terms of virial expansion. Now you see that is at finite temperatures, that is temperature is not low, not very low, but it is finite. In that case, the specific heat of the gas is smaller than its limiting value 3/2 Nk. So its limiting value is 3/2 Nk, but if we look at the whole series, then we can say that at finite temperatures the value of the specific heat will be a little bit lower than its limiting value 3/2 Nk at high temperatures. You see, this was the limiting value of CV. CV is equal to 3/2 Nk for classical ideal gas. For classical means when temperature is very high. So for that case CV is equal to 3/2 Nk for classical gas. But when temperature is finite, not infinite, when temperature is finite, in that case the value of the specific heat will be little bit lower than 3 by 2 nk, which we can say from this particular series. And as will be seen in the sequel, that is when we will discuss other part of the for the discussion Fermi system, the specific heat of the ideal Fermi gas decreases monotonically as the temperature of the gas falls. So we will show that step by step, that is, and the specific heat of the ideal Fermi gas decreases monotonically. You have to remind that decreases monotonically as the temperature of the gas falls. This we will show, this will again show and explain that is why it is so later on. So right now what we have discussed so far, that is mathematical preliminaries which we require for the study of the ideal Fermi system, and we have shown that is if we consider the classical case, classical means temperature will be very high and the density of the gas will be very low. So that is the classical and non-degenerate case. For the classical and non-degenerate case, these are the different expression for the thermodynamical variables of the ideal Fermi system. So these are the expression that we have derived, and I hope you have understood my lecture. The whole content of the lecture has been taken from the book of Patria and Bill, and I request the viewers to go through the book of Patria and Bill for further understanding. And I thank you all who have listened this lecture.